In Chapter 19, we're going to talk about electric potential, also known as voltage, or volts. And you can see she's at high voltage right now. She feels it. Her hair is standing on end. It's got a lot of potential, electric potential that is, or voltage. Well, before we get into that, we're going to talk about a very much related topic, related to the point where it's almost the same, potential energy. And to get us going on potential energy, we'll start back with what we already know, gravitational potential energy, which is very much analogous to the electric potential energy or the voltage. So let's get into that now. Before we get into defining voltage, we're going to remind ourselves of what we know about conservation of energy. We can do that by checking out this problem. Dropping a box, 200 grams box from a height of 6 meters. And the question is, how fast is it going when it hits the ground? Alright, well, we could solve this problem using the equations of motions we developed way back in the day, way back when, for projectile motion. But it's actually easier, and you may remember that it was easier just to use conservation of energy. Well, how's conservation of energy working? Well, to ever get this box up here to the height we're going to drop it at, we would have had to do work on it. And what would the work on it be? The work on it would be the force times the distance we move it through. Here we're moving it through a distance of h. Yeah, up a height h. And that work would have been the force, here's the weight, which would be mg, h. That's the work we did getting it up there. And you may recall, then, we will get all that work back. That work will get converted to kinetic energy, or in other words, the work will be equal to the kinetic energy. Coming back down, that'd be the 1/2 mv squared. And that'll be equal to the mgh. So from here, they're asking for the speed. We could just solve for it. We have a common term. It's canceling off right there. And from here we see that the velocity is going to be 2gh square root. Great. How's that related to conservation of energy? Well, it's the same as conservation of energy. Conservation of energy here in a frictionless system is a statement of the fact that potential energy plus kinetic energy equals E, the total energy, is constant. Or we could call potential energy U and kinetic energy K. I prefer it that way, a little less stuff to write. So in that case, what would we say? Well, we would say that anywhere this has got to be true. So for this particular box then, the potential energy will be what? mgy. Well, here I define y to be the height and 0 at the ground level down there, plus kinetic energy 1/2 mv squared is equal to a constant. So initially, at the top, what's the energy? I'll call it E sub I. Initially, it's just mgh. And finally, at the bottom, where y is equal to 0, it's all equal to 1/2 mv squared. Right? At any place along the journey, the total constant energy is equal to mgy plus 1/2 mv squared. Only at the top and bottom is it, well, okay, so here I'm using the velocity to be a variable, just as y is a variable. But these are fixed points. So at the top, I know the velocity is 0. That's when it achieves mgh. And at the bottom, I know that the y is 0. And that's when it achieves the 1/2 mv squared, where here I'm thinking of the v as the speed. Since this is constant, this implies E initial is equal to E final. And that's where we got this. So just another step. You go right there to that. Now, what about for the ladybug? situation. There she goes, zip, zip, zip. She started from a height of 6 meters. Remember, this is a completely frictionless system. So she has the same energy at the bottom here, no matter how she gets down there. In other words, the ladybug's energy is given by the energy is equal to a constant equation. Ladybug's energy is always mgy plus 1/2 mv squared. She starts off with velocity 0 here from rest. She starts skating from rest. So her energy at the top is mgh, same as for the box, where here we're saying that the height is 6 meters. At the bottom, she converts all of that gravitational potential, that 6 meters up of gravitational potential, into kinetic energy at the bottom, same as the box did. Unlike the box, the ladybug doesn't go splat and hit the ground here at the bottom, but she just keeps skating back up to the same height because it's a frictionless system. We're not considering frictional forces. So she just skates back and forth, converting gravitational potential to kinetic energy, and kinetic energy to gravitational potential, back and forth, so on and so forth. But for the purposes of this problem, what's the speed at 0, like when this is ground, or what's the speed when she's at 0, is the same for both. So, same for both because it is. They have the same mass and everything else. Although we see the mass factors out of the problem, so that's great. Now we just need to put in the numbers. So any way you want to look at it, the situation is the same in both cases. Here, the first way I looked at it was just to say the work we did against gravity initially to lift the box was mgh. All of that work ended up becoming the kinetic energy at the bottom, the 1/2 mv squared. So I set them equal to each other. Conversely, it's equivalent to look at it this way, just to say energy is conserved. Thus, potential energy plus kinetic energy is constant. So initially, the energy was all potential energy, mgh. Finally, the energy is all kinetic energy, 1/2 mv squared. Since it's constant, those are equal to each other, and you get the same thing. mgh is equal to 1/2 mv squared. Solve for the mass cancels. Solve for v. Plug in the numbers, and here we get the velocity is 10.8 meters per second.